Welcome back, Algebra 2.1 students. We are going to go through functions today. I just want to remind you to continue watching these videos because they do correspond to the homework, and the homework corresponds to the homework quiz, and the homework quiz corresponds to the quizzes, and so forth. So please watch the videos. Go back if you haven't watched the arithmetic sequences. Go back if you haven't watched the geometric sequences so that you have a firm grasp on what are sequences. And so now you'll go to this video and watch how are sequences related to functions. Let's get started. We're going to go through the bell work. We're going to review some geometric sequences here so that you are thoroughly prepared for your homework quiz for geometric sequences. Of course, we're not going to go through this. And then we're going to go through the objective essential question. What are functions? How are they related to sequences? And then, of course, we're going to go through the examples for functions. We're actually going to learn a lot of different things. What's a relation? How ordered pairs make functions? Why are sequences functions? How can I graph functions? How can I find the domain and range of a function? And so forth. And then the closure, summary, and homework. Let's get to it. All right, I have these two examples that will more than likely be on your homework quiz. Let's go and start on this first one. So write the formula. This is the first thing they ask. Write the formula of the general, I'm going to put number 1 because that's the first thing that they ask. Write the general term of the geometric sequence. The second thing that they want us to find is use then that formula to find a sub 7, the seventh term of the sequence. And this, of course, will be my step 2. So let's go to step 1. Let's see what we're going to be doing. First of all, let's list out our variables. My a sub 1 equals 1.9. And then, of course, my a sub 2 is this. This is my a sub 3. This is my a sub 4. But what is my r? My r, this is the interesting case because usually we can just kind of intuitively see, oh, this is times this, times that, times that. But this one's interesting in that the r is not really easily found. But rest assured, you can always find your r by using a quick formula, and that formula is a sub 2 divided by a sub 1. This will always give you your r value, your common ratio. So what is a sub 2? A sub 2 is negative 5.7, and then a sub 1 is 1.9. When I divide these, I actually get an amazing number, my sister's favorite number, 3. And of course, I have a negative. Okay? So again, if you need to find your r, and it's not so easily found by just looking at the sequence, then you can use this quick formula, a sub 2 divided by a sub 1. Then, once you perform that operation, you should get your r. So what's my r? In this case, it is negative 3. Now, we have both of the variables that we need. This is my formula that we learned yesterday, my geometric explicit term formula. A sub n equals a sub 1 times r to the power of n minus 1. So let's start plugging this in. We want to just keep it in terms of n for this first one. Remember, our first step is just the general term of this geometric sequence, okay? Not the actual find the term. That's step 2. So I'm going to keep it in terms of n here. My first term is 1.9, and then times my common ratio is negative 3, and then n minus 1. So this is my general term of the geometric sequence formula, okay? It's going to ask you that first. The next thing it's going to ask you is, find a sub 7. So that means n, of course, is 7. So I'm going to write a sub 7. Everything else stays the same except for the fact your n, right here, 7, becomes, 7. Your n becomes 7. What does this equal? Of course, you can just plug this straight up into Desmos. You should. So if we go over here, let's type it in. I have 1.9, and then I have parentheses. I have negative 3, and then end parentheses, and then I'm going to go up. So most of you are probably also wondering, how do I get up there? Okay, there's a couple ways to get up there. So let's just go back. I have this, okay? If I actually go down and I click on this show keypad, I will actually bring it up to this menu, and this menu will show you squared. But let's just say I don't want a squared, right? So if I don't want a squared, then of course I don't want to put that. But maybe I just want another exponent, and so that will give me an exponent. Okay, I want to do 7 minus 1, so then parentheses 7 minus 1. Okay, so that is my answer, 1385.1. I'll go over here and I'll do 1385.1. 1385.1. So that is my actual A sub 7. But let's go back real quick before we move on. I wanted to show you that this Desmos thing is amazing. It has tons of menus here. So this menu is just found at the bottom. I know my tools are kind of hiding it. So if I unhide them, it's just right here. So you can just toggle that on and off. But that is where you find the exponent there. Okay? Remember to use parentheses when you're putting in exponents. Okay? So I just wanted to show you that just so you don't forget. Let's get back into it. What is the next problem? A professional baseball player signs a contract with a beginning salary of $5 million. Wow. That's amazing. So first of all, before I even move on, I'm going to start labeling my stuff because this is definitely A sub 1. So 5 million, that's 6 zeros attached to it. I still need to find my R, right? Because that's geometric sequences. 5 million the first year, like I said, A sub 1, in an annual increase of 6%. Now, some of you may be thinking this, 6%, that's 0.06. That's your R. Wrong. Okay, keep reading. Beginning in the second year. So it explains it a little bit more. That is, beginning in year 2, not starting year 1, but beginning in year 2, the athlete's salary will be 1.6 times what it was the previous year. So what does that mean? That means my R is not 6% or 0.06. It is 1.06 because you're kind of skipping a year ahead. And so the first year is literally just 1. But then the next year, starting year 2, it's going to be adding that 6% over to that 100%. Okay? So this is actually 106% that he's getting over and over and over again every year. That's pretty crazy, but it's really not going to be that much. Let's start writing it down. I'll show you what it is. Athlete salary, year 7. So, of course, we want to use n equals 7. So A sub 7 is 5 million. That's my first term. And then my R is 1.06. And then 7 minus 1. Let's go to Desmos. Let's see what's happening here. All right, so I go to the next one. You can exit out of that one if you want. Let's do it. So I have 5 million, 6 zeros, times 1.06, not 6%. And then I want to do 7 minus 1. And I get this big fat number in the millions, all right? He's a baseball player. He makes some big dough, I'm telling you. Nice cheddar cheese. All right, so let's write this down, rounded and using money. So this is 7,092,595.56. So this is rounded. I'm pretty sure Math Excel will ask you to round it, so that's why I'm rounding it for you. No need to applaud me, okay? So that is your actual final answer. It may actually even ask you to round to the nearest dollar, but whatever it asks you to round to, make sure you round. That's my final answer. How are you feeling? You feeling good? I hope you're feeling good. If not, replay the video. If you are, let's move on. I'm going to erase. Great. So geometric sequences, I'm going to give you 25 minutes on this one because they can be a little bit more tricky. So 5 questions, 25 minutes. Of course, open notes. Remember, always send me partial credit. Just send it to me. Just put, hey, this is the homework quiz, geometric sequences on the subject. And then just say, hey, on this question, I accidentally put this, or maybe I put this but really wanted that. Can I get partial credit? Just ask that, and then I will definitely look into it. I have the sole authority to say yes or no, and oftentimes I won't even respond to you, but you'll see whether or not I have given it to you on Synergy when it says corrected. So if you see on the comment on Synergy when I grade the homework quiz geometric sequences, if I put corrected there, that means you know I at least gave you some partial credit. Once you're done with that homework quiz, go ahead and start your Cornell notes for today. This is a rather fun lesson. I think it's fun because it's making connections, and I hope that we're making connections with mathematics. That's why math is amazing, because we make connections. Okay, so please pause the video if you need to, do the homework quiz. Let's get started on the functions. All right, so what are we going to do? First of all, you're going to see functions everywhere. Okay, there's going to be tons of functions. We're going to learn so much stuff, and I'm going to try to summarize it to the best of my ability at the very, very end, but we are going to blow through a lot of it, like go really, really fast. So try to keep up. This will probably be about 40 minutes to 50-minute lesson. Okay, what is function notation? Why is it important? We should know how to identify function at the end of the lesson, use function notation by recognizing specific characteristics from functions and its graphs. All right, how do I use function notation? Let's get to the big boy Algebra 2 stuff. Boom, let's do it. Functions, patterns, and sequences. How do patterns and sequences, how do arithmetic sequences specifically relate to functions? Let's find out. Write the explicit formula for the following arithmetic sequence. So before I get started here, obviously, I'm going to write out my formula. So this is the formula for arithmetic sequences. I cloud it because it's a formula, not my answer. And so now what I want to do is look at my sequence. How is this differing from one term to the next term to the next term? Now remember, I have a common difference. Okay, my common difference will be different than the ratio. Remember, I'm adding or subtracting. And you should say, well, there's plus 3 here. Plus 3, plus 3. So my first term, of course, is 1. That's the very first one I see. That's my first term, a sub 1. And then my common difference, we just said, was 3. Now, I got my formula. I analyzed my sequence. I got my variables. What do? I'm going to put this in the general form or explicit formula. So I'm not going to actually know what n is because it doesn't ask me find this any given term, right? It just says find the formula. So let's start plugging this junk in. I have a sub n equals my first term right here, we said was 1 plus my n. Remember, I'm not going to touch n. Okay, I'm not finding a specific term. I just want the general formula. Okay, minus 1 and then times d, which we said was 3, so I times 3 there. Now, of course, just like any other distribution, because of the commutative property, I can multiply this through. So what do I have? I have 1 plus 3n minus 3. And what does this equal? When I simplify everything, specifically those two, I have 3n minus 2. This is my general term formula. Now we're going to come back to this. So I'm going to start. And we're actually going to come back to this sequence in particular throughout the rest of the slides. So I would definitely be writing down in your notes, getting prepared. Make sure you start this because we're going to come back to it a lot. Okay? Now think about it. Find the following terms of the sequence. Now we're interested in finding the specific explicit terms of this sequence. Okay? Whoops. Let's go down. I guess I didn't write it, but that's okay. Let's find a sub 5. Let's do that. Let's find a sub 100. Ooh. And then let's also find a sub 2. Let's do that. Okay? Awesome. Actually, let's add a couple more here. Let's just do the first 5 since we're already going to do it, and then let's do 100. So let's do a sub 3, a sub 4. Whoops, I'm not doing really hot right now. a sub 4, and then yeah, let's do that. Let's do all these. A sub 5, 2, 3, 4, 100. I already found no, we didn't find a sub 1. Let's just do that. Man, this is awful. All right, let's do a sub 1. What do I do? Well, the first thing I do is I can now use this formula. So let's do this formula. I have 3 here, and I'm actually going to plug in 1 because my first term is 1. I'm going to plug my first term in there. So, okay, I already know that it's 1 here. But just because I already know it's 1, we can still use the formula, okay? Now, what happens when I plug in this 1 right there? If I plug in that 1 in for n, I have 3 times 1 and then minus 2. Again, following this formula. What does that equal? This, of course, equals 1. Now, couldn't we just look at our sequence here and just say, yo, Mr. Carlson, you joking? It's freaking 1. Yeah, you could. But what if you don't have a sequence? That's the problem. Okay, so now let's go to 2. Now, obviously, we know it's 4, right? That's okay. All right, but let's just go for it. I'm plugging in 2 for n, and then minus 2. What is this? That's 5 minus 2, and this is 6, sorry, 6 minus 2, and that is 4. So obviously it's 4. A sub 3, what is a sub 3? If I plug in 3 here, that's 9 minus 2, this is 7. Does it match our sequence off to the side? Yes, it does. A sub 4, it should be 10, so 3 times 4, and then minus 2, so that's 12 minus 2 is 10. Yes, it matches. Now we don't know a sub 5, so let's find out. I take 3 times my n, in this case it is 5, and then minus 2, and this becomes 15. This is minus 2, so what is it? 13. What is 100? Well, let's find out. So I plug in 100 here, minus 2. This is going to be 300 minus 2, and this is 298. All right, so I have all this stuff. Now pay very close attention. You ready? Now, let's look at a sub 1, 2, 3, 4, and 5. Watch. This is 1, 4, 7, 10, and then 13. We have a common difference of 3. We should have already known before, because we are familiar with arithmetic sequences and the recursive formula, that we use 10 and then plus another 3, and that gives me 13 for my 5th term. We didn't need to go and use this formula. But why did we use the formula? Because it's a function. Watch. Watch very closely. What does this function, not sequence, function look like? This literally is y equals 3x minus 2. It is a line. It is a line. Isn't that crazy? So now watch, look at this 3 here, and then look at this 3, look at that 3. The 3 is the common difference, right? But if we put this in a linear slope-intercept form, what is this 3? You should all be saying, Mr. Carlson, that's your slope. So if my slope is 3, and I know that this linear function is the same thing as this arithmetic sequence, what is my common difference? It is my slope. My common difference is slope, the constant rate of change. That's what slope means. A constant rate of change is the same thing as a common difference with sequences. And so now what we're going to be doing today is looking at how we go from arithmetic sequences specifically and the notation of arithmetic sequences into what we call functions, function notation, and the arithmetic of functions. Okay? Because we should know and very clearly see that this right here, this sequence is a function. And I can do the exact same thing. I could plug numbers in for x and get something out, which is what we will be doing right now. So let's move on. Keep that in the back of your mind here, because we're going to continue and seeing how functions relate to sequences. First off, what is a function? We already know kind of what a sequence is. It's a pattern, but what is a function? Well, a function, of course, is a pattern, but it follows a specific pattern. And it is this: a function is a correspondence from a first set called domain. That should be very familiar. A domain. This is also what we call our x values, by the way. Okay, so x. It's also what we call, whoa, that looks a little bit too ambitious there. It's also what we call our inputs. So I'm going to write that. So our domain is our x values or our inputs. So correspondence from a first set domain, okay, x, to a second set called range. What is my range here? My range are what we call my y values or our outputs, what I get out. So what happens here? Think of a function like a machine. It functions correctly. Your cell phone is a function because it corresponds to certain things. If you touch its screen, it's going to register that you touch the screen and put something out there for you. So let's just say I click on my Facebook app. I use my finger, the input, and then what comes back out is the actual Facebook app. You'll start seeing your news feed and whatever. Same thing with Snapchat. You take a picture, you use your thumb to put the input. Your cell phone registers that that's an input, and then the output is what? The effect, right? The effect. That is taking the picture. Okay, so your cell phone is itself a function. It's registered with inputs and outputs. Okay, but here is what truly makes a function. And now watch this. Such that each element in the domain corresponds to exactly one element in the range. Okay, each element in the domain corresponds exactly to one element in the range. In other words, you can't have multiple outputs. Okay? Why do I say that your cell phone is a function? Because if you press something, okay? If you press something, do you have multiple apps just popping up everywhere? No, because then it's not functioning properly, right? So what makes it function properly is if you have exactly one element in the range, one element that's outputting. Okay? I can have multiple fingers on my screen, okay? But usually only one thing will register. So if I have my app screen right here and I touch my whole hand on it, usually the first thing that happens is the first app that my hand touched, that will register. But is it multiple apps? No, it's one app. So for every input, no matter how many inputs you have, there's only one single output that corresponds to one single input. Okay, I'm going to continue hammering this home, but let's go back to our previous example. Write the set of ordered pairs from an arithmetic sequence, or what we call a relation. So what does that mean? An ordered pair is what we call a relation. And then we're going to ask, is it a function based off of this definition? Okay, so let's find out. I'm going to write my fancy braces here, and we're going to actually start listing these. Now go back. We got our first term, a sub 1. So watch this. A sub 1, what did I get out for a sub 1? What was my first term? My first term, we got out, when I plugged it in, the function, we got 1 out. Again, go back through your notes. Okay, we did this. I'm just going to briefly show you. A sub 1, this was 3 times 1 minus 2. And so this was 3 minus 2, and this is 1. Now watch this. This is our input. Okay, this right here is our output. If I can spell it correctly. Wow, look at that. Dude, don't tell anybody. Okay, this is your output. Is that better? Oh, yeah. Okay, output. All right. So this is our output. So what we plugged in, a sub 1, right here was our input. Our output was literally what we got out. The thing that popped out like a freaking baby. Okay, we all know what the input is when we have kids, yes? Okay, how we make babies, and then the output, we should know what goes on with the output, the pushing of the baby. Okay, so same thing there, input, output. So now, what was a sub 2? When we found a sub 2, what was our answer? It was 4. When we did a sub 3, what was our answer? When I plugged 3 into that sequence and that function, we got 7. What was a sub 4? We got 10. Now we did a sub 5, and again, we got 13. And then we jumped all the way to a sub 100, just cuz, and then we got 298. Okay, now watch this. Watch. Look at this. A sub 1, A sub 2, A sub 3, A sub 4, A sub 5, A sub 100. Okay, so this is A sub 1, this is A sub 2, this is A sub 3, and so forth. Now watch this. This is 1, 4, 7, 10, 13, and blah, blah, blah. Okay, so watch. From here to here, what's the difference? 3. From here to here, what's the difference? 3. From here to here, what's the difference? 3. What was my common difference? Oh, yeah, it was 3. What was my slope? 3. Okay, so this is how sequences, arithmetic sequences specifically, relate to linear equations. How arithmetic sequences relate to linear equations. Okay, so this is all the ordered pair. I'm not going to erase all of this. I'm just going to erase some of this. So just bear with me. I don't want to pause the video right now. All right, let's go to town. All right, the domain of a function is a list. Oh, shoot. Before we get here, I forgot. Let's analyze whether or not it's a function. Okay, how is it a function? How do I know? I need to answer that in purple. Is this a function? Are these relations, these ordered pairs, is it a function? Great question. Remember what the function is. The domain are x values. This is an x, that's an x, that's an x. This is an x. Each domain corresponds to exactly one output. What does that mean? You can't have repeat outputs. Okay, so what is a function? I'm going to put it up here, guys, because I know this can get kind of confusing. You'll probably be like, what is going on? Okay, a function equals no repeat outputs. That's probably an easier definition, right? Yes. So this is what a function equals, no repeat output. So do I really even care about what the x's are? No. Okay, I don't. So those are my x's, yes, but look at my y's. That's 1, that's 4, that's 7, that's 10, that's 13, this is 298. So far, are there any repeats, yes or no? No, which means if there's no repeat outputs, is it a function? Yes. Okay, so this is what we call a function. Yes. Smiley face. And of course, a nice little fat unicorn to go with it. Good deal. All right, now what we can do is go through the next question. What does the next question say? The domain of a function is a list of all inputs. What is the domain of this arithmetic sequence we just did? Let's list them out. I'm going to use my fancy braces. Again, the inputs, so the first number. So it's 1, 2, 3, 4, 5, and we also had 100 in this. Okay? And now the next one is going to ask, what was the range? What's the range? The output values. Okay, what's the range of all the values of the arithmetic sequence that we just did here? What is that? Okay, if you need to catch this out, it's just, you can pause the video right now and get that little piece. It's just the output, okay? So that means my range is literally 1, 4, 7, 10, 13, and 298. Now the range in the domain can be really anything. It could be unicorns. They could be white people. I mean, literally anything. It could be pie. It could be food. It could be numbers. Obviously, this is number because a set is just anything. And usually in math, we do sets of numbers. So I hope that helps. I hope that kind of introduces what a function is, how I know something is a function. Let's erase, and then let's actually get to the big boy math notation of a function. Okay, now, first things first, guys, remember mathematics is a unique language. It is literally a foreign language. To me, it's no different than Spanish. I mean, seriously. Some of you are probably thinking like, dude, for real? Yes, for real. Because it is a language. You just need to understand the language, okay? And we don't do a good job teaching the language. When you read symbols, they are literally just a language, just like the Aztecs. The Aztecs had symbols for their language, but they communicated through that way. Math is the same thing. It is a unique language through symbols, and we need to be able to interpret that symbol because it communicates to us an action. It says do this, and if we don't know what that means, then can we even do the math? No. Okay? So we need to be able to understand the language in order to understand the mathematics that's being communicated. So, what's going on here? Right here, this was our sequence. This is the big boy math notation of what it actually means. So I'm going to read it. A sub n equals 3n minus 2. This will now become f of n. F of n. So a sub n, f of n. F of n equals 3n minus 2. That's how you read it. Okay, f of n. What does the f stand for? Obviously, function. F stands for function. A standard for arithmetic sequence. Okay, so a sub n equals 3n minus 2 will now become f of n equals 3n minus 2. Now watch this. We can now evaluate or find the range, the y values of the functions using the following symbols. Now watch. When I say evaluate, what I mean is find the output. Find the range. Find the y value. They all mean the same thing. Output, y value, and range literally all mean the exact same thing. So when it says evaluate the function, you're going to be thinking, what's the output? Okay, that's what you should be thinking. What is my y? All right. So what are the following symbols? I have f of 7. I have f of negative 5. And I have f of 0. Let's use this function right here and go to town and do some good stuff. All right. This function right here. Let's start going to town. So f of 7. I'm going to plug in, what this means, I'm going to plug in 7 for n. Okay, f of 7. So that means 3 times 7 minus 2, which of course will become 21, minus 2, which then becomes 19. Okay, that's what it becomes. Now what did I do here? Look at this. This 7 is my x or my input. And if you're thinking like, silly Carlson, that's n. Yes, means the exact same thing. Okay, n is our input. Okay, but when we start transitioning from a sequence to an actual function, we're going to drop the n and start going through x. Okay, so I'm just going to put x here, input. So whatever you see in parentheses here, that's your input, the input of your function. What your output is what you got. So when you evaluated 19. Let's continue. So this is 3 times negative 5, then minus 2. This becomes negative 15 minus 2, which is negative 17. Okay? Negative 15 minus 2, which is negative 17. All right. Now let's do 0. So 3 times 0 minus 2 equals, what is this? Negative 2. Now I want to kind of pause here, and I want to emphasize this. Kind of pinpoint f of 0 here. Now watch. Watch, 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 watch. If I take this and I do this, guys, this is y equals 3, let's just say it's 3x minus 2. What happens if, watch, if I plug in 0 for x? Just like what I did here, right? What happens if I plug in 0 for x? Just like what I did here, nothing's changing. I get, what do I get? Negative 2. So I get y equals -2. Awesome. So what did I plug in? What was my point? What was my input? Well, I inputted into my function 0. Okay, what was my output? Well, Mr. Carlson, we got -2 out. Great. Look at this. Look. What is this? 0, -2. If I plotted this on an actual XY plane, which we will in a little bit, 0, -2 is right here. Which axis is that on? You should all be seeing the y-axis. Watch. Look at this. Why in the world, when we looked at a function like this, in Algebra 1, did the math teacher just say, okay, -2 is your b value, and your b value is your y-axis value, so you plot that at -2, and then you go up 3 over 1, and so now it's going to look something like that. So why did he say that you're going to start here at -2? I'll tell you why. Because it's a function, and guess what? If I plug 0 in for x, I get -2, my b, for y. And that's exactly what I have here. So not only are sequences related to functions, but this function notation is actually something you've been doing for a long time, but just behind the scenes. But now it's Algebra 2, and we're using some big boy mathematics instead of little boy mathematics. And now we're going to actually be making the dots, making the connections, connecting the dots, making the connections, and seeing how they relate to each other. You guys did this in Algebra 1 all the time, and you just said, oh, that's the b value, I plot that. But you had no idea why you plotted that. And that is a shame. Okay, the reason why you plotted -2 on your y value is because the point itself is 0, -2. And if you put 0, -2, that's your input right here, this 0. That's your input. And what you get out of your function is -2. That's why it's your y-intercept. That is why it's the b value. So I hope that sort of makes sense. Maybe you just tune me out because I'm yelling too much and you just hate me. Or you're like, wow, this guy's really intense. I'm passionate about you guys making connections. That's all. So what does this mean, guys? It means a couple things. First off, if I have an x and a y, okay, this can also mean this. This is the big boy mathematics. So instead of using x and y like in Algebra 1, used it in Algebra 1, we're going to do this. Algebra 2. Okay, what does f of x mean? So x is the input. Okay, x is the input. F of x is the output. Okay, so this right here is my output, and this right here is my input. So I'm just going to change my y instead of f of x, which means this, guys. Does y equal f of x? Yes or no? Yes, okay, it does. So whenever you see f of x, just think of it as y because it's the exact same thing, okay? All right, I'm going to erase all this. I'm going to have one last thing that I want to say right here. I already kind of said it. X is the input, f of x is the output, okay? So if you don't already have that, please put that there. Let's move on. Let's go to town. What is function notation? If I have a function like this is actually a quadratic. F of x equals x squared plus 3x plus 5. Okay, what is this? It's going to be asking you, find the following range values, output values or y values. Okay, how do I do that? Okay, if I have f of 2, what does that mean? It means I'm going to plug in 2 in this x and in that x. Because 2 right here is what? This is my input. 2 is my input, my x value. Okay? That's my x value. Notice I'm using x's now instead of n's. Now we're going full on function. No like lefty, righty, arithmetic sequence junk. Let's start plugging it in. So I have 2 squared, okay, plus 3 times 2, and then plus 5. what does this equal? This will equal 4 because 2 squared is 4. This is equal 6 and then plus 5. And then I can add them all together. This equals 15. Okay? Awesome. Notice I put parentheses around the squared part. Okay? Make sure you do that. Put parentheses around the squared part. Now, what if I have something like this? N plus 3. This one's a little bit more complicated, but I think we can do it. Now, watch. We're going to do purple. I'm going to put n plus 3 everywhere I see x, which means in parentheses, I have n plus 3 squared right here. Okay? So what did I do? I literally substituted, guys. I substituted that whole thing, the n plus 3, inside of that x, because that's my input. N plus 3 is my input inside of that x. But that means I need to square it. I need to square afterwards, and that's what I will do. Okay, so I square that junk, and now what do I have after I finish it? The rest I have plus 3 times, again, right here, n plus 3. So I have n plus 3, and then plus 5. Now let's start simplifying this, okay? I'm going to simplify this. How do I do the squared part? What does it mean to have something squared? If I have 2 squared, what does that mean? It means 2 times 2. If I have 5 squared, what does it mean? It means 5 times 5. If I have 10 squared, what does it mean? Okay, Mr. Krause, we get it. 10 times 10. Great. What is n plus 3 squared? You better not say n squared plus 9, because that's not right. Okay? It is that thing that's in parentheses times itself. Okay, so that means I have to do n plus 3 times n plus 3. Now, some of you probably haven't seen this mathematics in a long time, okay? But don't worry, that's why you have me. I'm going to distribute this right here because that's what it means. So plus 3n plus 3 times 3 is 9, and this is plus 5, okay? Now, what do I do here? What I do is what we call, if you remember, FOIL, okay? First, outer, inner, last. Okay, first, outer, O, inner, I, last. So first, what does that equal? N times n is n squared. Not 2n. N plus n is 2n. But n times n is n squared. So then I do my outer terms. Okay, n times 3 is plus 3n. I do my inner terms. 3 times n is again plus 3n. And then I do my outer term, or my last term, sorry, my last. 3 times 3 is plus 9. So that's what it looks like when I FOIL it all out. Maybe some of you remember that. I'm going to start combining some of this stuff. So this is plus 3n. I'm going to take that down the bottom. I can combine this junk right here. 9 plus 5, that's 14. Now, let's start simplifying. Okay, I can combine this, and then I can combine the 9 and then the 14. So I have n squared plus 3 plus 3 plus 3 gives me 9n plus 9 plus 14 is not 15. Wow, I was thinking 15 because 9 plus 4. That's not even 15. Wow. 23. That's 13. 9 plus 1. I don't know why I was thinking it. Boom. That is my final answer. Now, if you are struggling with that at all, I encourage you to just rewind the video, go over it again, okay? But Math Excel will ask you to do something like this, and you will have to FOIL it out and just combine like terms. Okay, the only 2 things I did here is, number 1, I FOILed. And then number 2, I just combined. Okay, I just combined like terms. That's really the only things that you need to know how to fill or complete this problem out. So I just FOILed the first thing and then combined like terms. That's really all that problem is. Okay, I think I have one more. I think I have on this page. Yeah, I have f of negative h, but I'm going to move it over here, so I hope you don't mind. Okay, so f of negative h. This is my third thing that I need to do. Let's just keep it in purple, I guess. So what does this mean? I'm going to put a negative h everywhere I see an x. So in parentheses, negative h, and then squared, because my formula says squared. Make sure it's in parentheses. They are your very best friend. Plus 3, your best friend comes back with parentheses, negative h, and then plus 5. Now, when I square something that's negative, what happens, guys? Ha, 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 ha. What happens? Becomes a positive. So actually, I still have h squared here. Now, some of you are wondering, well, why don't you just have h? Well, because I don't know what h is, and I definitely don't know what h squared is, okay? And so I don't put just h here because the squared doesn't do anything. It would do something if it was a number, but since it's a variable, it doesn't do anything. But what I do know is this can never, ever, ever simplify down to a negative, so I can just make that into a positive and then make sure that that's a positive as well. They know no matter what number it is, it's always going to come out a positive. So I'm simplifying it. Positive 3 times negative h, that gives me a negative 3h for sure. And then this is plus 5. So this right here would be my simplified answer. All right. That is the basics of function notation, of evaluating functions. Let's get a little bit more funky into graphs of functions, and then we're going to start analyzing functions, and then we'll be done. Okay? Again, pause the video at any time. I'm going to erase. Okay, graphs of functions. What do graphs of functions look like? Once we have a function that pairs two numbers together, we can plot them on a graph. So we want to plot the function or arithmetic sequence that we started with. So what was that? We started with this. So 1, 1. I'm just rewriting it. We're coming back to that original relation, the original ordered pairs that we had on like the second slide. And then we had 3, 7, and then we had 4, 10. Okay, I'm going to leave the 100 out and the 5 out for now. Okay, but these are some of them, not all of them, but some of them that we did. All right. Now let's graph this beast. Okay, 1, 1, it's right here. Boom. Okay, 2, 4, 2, 4 is right here. Boom. 3, 7 right here. And oh, 1, 1 is right here. Sorry. I'm not thinking correctly. Where is the last one? 410. Where's 410? 410's all the way up here. Now that you start to see what's happening here, we have a slope of what? So 1, 2, 3. So 1, 2, 3 over 1. So we have a slope of 3. So now we can kind of combine this. So 1, 2, 3 over 1. And what do you know? This was our actual function, by the way. Actually, I'm going to not use y equals. I'm going to use f of x because that's big boy notation. So we had f of x equals 3x minus 2. This came from this sequence, okay? But now we're using in not sequential terms, but functional terms, okay? And notice, what's my b value? Negative 2. Remember, it always will cross right there. Like I said, my slope is 3. Okay, now I can sort of combine. Maybe this will be an awful. Maybe this won't be that great. That's not that bad. And then it kind of trailed off at the end. Smiley face. Okay, so that's basically how I would graph the points. Of course, this is easy. I already know it's a function because I looked at the ordered pairs. The ordered pairs, they don't have any repeated y values. So since they don't have any repeated y values, it's a function. But hey, there's another way to find whether or not it's a function, and it's called this, the vertical line test. So let's just say you graph a function, right? If you graph this function, is it a function? It says if any vertical line intersects a graph in more than one point, the graph does not define y as a function. So if it goes through any point more than once, if I do a vertical line all the way through the graph, if it hits 2 points of that function, it is not a function. So let's test it out. What does that mean? So I usually tell students this: put like your pencil, your pen, and just kind of put it right here and just kind of trail along. Just trail along that value. So I want to see if I can actually, will this work? No, it won't work. It really won't work. Whatever, I'm just wasting my time. Let's do this one. Okay, but if you know, since I can't really do that, try doing this. So just trying to do like vertical lines, just dotted vertical lines. Okay, so it hit once here. Let's do this one. It'll hit once here, so I'll put an X. Okay, and then I just keep going, and we start seeing it's only hitting really at one spot, right? So it hits spot right here, hits right here, hits right here. But is it hitting more than one spot? Is it hitting in more than one spot? No, it's just hitting here, 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 and it's not hitting in more than one spot. So that means, yes, we can consider it a function. Now, some of you are thinking, well, what does it look like if it does hit in more than one spot? I'll show you. Actually, I'll erase everything. So get this down and I'll show you on the actual graph. If it's not a function, it's going to look something like this. So this is actually an inverted parabola. Okay, an inverted parabola. So if I have y equals x squared, okay, so I'm going to erase that. That looks like garbage. If I have y equals x squared, and let's just say I do the square root. So now what I have is this, x equals, okay, the square root of y. Okay, x equals the square root of y, or something like that. Or even if I have y equals radical x, okay, which is this actual function. This is what it's going to look like. Now watch this. Watch. The vertical line test right here. If I go right here, how many times does it hit? Well, it hits once. But right here, watch. It hits once. It hits twice. Here, it hits once. It hits twice. Okay? It hits twice right here. Again, once, twice. So because it hits twice, this is not a function. No function at all. Okay? So that's kind of the difference between how to use the actual relations, the ordered pairs, and just kind of abstractly thinking about it. We did that in the earlier couple slides by, okay, it doesn't have any repeating y values, therefore it's a function. Or you can graph it, let's just say on Desmos. Okay, you don't need to graph it by hand, but you can do it on Desmos, and you can see if that vertical line test actually does fulfill it. Okay, awesome. So I'm going to erase. That is how you find if a graph is an actual function. If a graph is an actual function. Now let's get into, and this is where we're going to be probably spending the rest of our time. I'll be going probably through the first couple ones pretty fast, but how do I analyze functions? How do I analyze functions, specifically graphs of functions? Okay, so first thing we're going to do is we're going to see what the domain is. What is the inputs? What are the domain? What is the domain? And we're going to put this in interval notation. On the first couple ones, I'm probably going to show you what it looks like with set notation as well. Okay, we may be a little bit familiar with that using absolute value inequalities. Last week we looked at set notation and we also looked at interval notation. So I may do both just for a little bit, but I'm not gonna continue doing both. We're also gonna find the range, obviously the interval notation of that. What are the intercepts? Where does it cross the x or the y axis? And then also we're going to evaluate specific points. And by evaluation, I mean we're going to be given a point, an input. F of 1, what is that? So we're going to be given a lot of funky graphs, and the first funky graph that we're going to be given is this. Now, I don't know what this function is. I don't know what numbers go into this function. All we know is y equals f of x, which means that's the same thing. It is some function. I don't know what it is, nor do I care. I don't care what that is. What I do care about is this. What is my domain? My domain is reading left to right. We said that last week, yeah? We read math left to right, okay? Left to right. So that means when I look at my domain, watch this. Does the graph exist right here with -5? Yes or no? You should all be saying, no, it doesn't exist, right? -4. Now notice I'm starting at the left side. I'm not starting all the way over here. I'm starting on the x because domain corresponds with my x value. I'm starting at my x value, and I'm starting right here at the -5 because left to right. Okay, starting with the negatives first. Doesn't exist here. What about -3? Doesn't exist there. -2? It does exist here. The graph not only touches the x-axis, but yeah, it is existing. So that means with interval notation, you ready? Since this is a closed dot, it starts existing bracket 2. Now remember, just as a refresher, brackets mean included. Okay? Parentheses mean not included. So these are like open dots. Okay? So bracket, because it's included, comma means going to. Now watch, I'm going to go, and still my graph is existing. I'm trailing along my x-axis, trailing along, because my x-axis is domain. Trailing along, right? Okay? So far, so good. Now, where does the graph stop existing? It stops existing right there at 1. And notice I'm pulling out my x values, x, -2, x, 1. I'm not doing anything with my y values because I'm on domain. Domain is my x, my input. Okay, so where does it stop existing? It stops existing at 1, and since it is a closed dot as well, we're going to be putting 1 closed dot. Okay, what does this look like for set notation just for kicks and giggles? Okay, just for kicks and giggles, looks like this. X, the domain of x, of all x, such that it's between 2 and 1. So that's what that looks like for the set notation. I'm probably only going to do it for this slide because I don't think Math Excel actually asks you to do it, but yeah. All right, let's erase all of this. Let's move on to my range. What is my range? My range is different. Now I'm not going to be looking at my, my left to right. I'm going to be looking at from bottom to top. So I often say domain, we read from left to right, but range, we read bottoms up. Okay, bottoms up. So bottoms up, that's how we do it. Bottom, starting at the bottom with the negative, going up. So you have to ask yourself one important question because we are looking at my y's. So we're looking at my y now. Does the graph exist right here? No. Here? No. Here? No. Here? No. Here? No. Where does it start existing? Right here. Because this is where it actually touches, right here. It actually corresponds to a value right there. Now, what does that mean? Okay, what does that mean? That means it starts existing at which y value? And which y value is that? Well, let's look. This is -1. What's that y value? 0. So where does it start existing? 0. Why do I do brackets? Because it's included. Where does it stop existing? Still exists there, still exists there, still exists there, stops existing there. Okay, so what's the last number here? 3. So right here at 0 and then 3, that's where my graph exists. For set notation, it looks something like this. Set of all y's such that y is in between 0 and 3. So it looks something like that. Okay. Again, I'm not going to really do set notation that much at all because I don't think Math Excel asked for it. Let's go to my intercepts, and I promise these are going to be a lot faster as we kind of go through. Intercepts. Where does it cross my x-axis? Does it cross my x-axis at all? You tell me. You should say yes, it does. At what value? What x value does it cross? -2. Right here, -2. So that means I'm just going to put -2 here. Okay? Y, where does it cross my y? Right here at 1. It crosses there at 1, so that's my intercept. Now, evaluate f of 1. Now, what does 1 mean? 1 means input. Okay? 1 means input. So that means I'm going to look at my graph, my input of 1. This right here is f of 1 right here. Okay, so now what is my output? Because I want to find what it equals. And so what is this? It's 3. Okay? Boom. So what does this mean? This actually means, guys, this is a point. 1, 3. So when I say 1 comma 3, this actually literally is the same thing as saying, okay, this is the exact same thing as saying f of 1 equals 3. So these two things are exactly the same thing. But most of the time we're used to these ordered pairs, but that's what we did. We just found, okay, if f is 1, what is my output? Okay? Or if x is 1, what is my f, my function output? And that's 3. So get that down. We're going to go through a lot more of these, probably like, I would say 4 more, and then we're going to be wrapping it up, okay? But I'm going to go super fast through them. So let's erase. Let's go to the next one. Same exact stuff, different evaluation, a little bit more easy graph. So let's go to town. What is my domain notation? My domain interval notation. Left to right, where does it start existing? It starts existing on my x-axis right here at -3. Now, is that closed or open? It is open, so I'm going to write parentheses, -3. Where does it stop existing on my x-axis? It stops existing here. Okay, so it stops existing right here. And that point, don't look at this point. We're looking at our x-axis. X-axis is domain. Okay, x-axis is domain. Don't look at that. We're going to look at this one. It stops existing there at 2. And since it's closed, I'm going to put a bracket. Awesome. Okay, now let's go to range. We don't read it left to right. We read it bottoms up. So we're going to ask, does it start existing down here? No. Right about here? No. Right here? No. Where does it start existing? When I'm reading my y-axis, it starts existing at 1. So that means I'm going to put 1. Since it's not closed, I'm going to put open dot. Where does it go to? It stops existing right here at 2. Okay, so 2, really, really small. And since that is a closed dot, I'm going to put bracket. I hope you're trying to get the hang of this, okay? But this is really what it means. This is what the notation is. Again, this is big boy mathematics, okay? Does it have any x-intercept? Actually, no, so we're just going to put none. It doesn't intercept the x-axis at all, but it does intercept the y-axis. It intercepts the y-axis right here. Right here. Where do you think that is? Probably like 1.5, maybe 1.7, something like that. So I'll probably just do 1.7. Okay, somewhere around there. F of 2, what does that mean? It means I'm going to look at 2 because that's my x. Remember, 2 is x right here. That's always going to be my x value. I look at 2, and then I want to see where does it kind of correspond to my graph. My graph, it corresponds right here at 2. So that means f of 2 is 2. And this is the same thing as saying 2, comma 2. Sweet. Let's move on. Okay, we're going to go to town because a lot of your assignment is just this. So let's erase. Let's continue. Let's get another funky one. It's kind of like half a parabola. Kind of deteriorated a little bit. My domain, left to right, right? Yes, left to right. Where does it start existing? It starts existing right here at -2 since it's closed. Brackets. Okay? Keep going, keep going. Where does it stop existing? Right here at 1. And since it's an open dot, I'm going to put parentheses. Now, for my range, what about my range? Not left to right, but it's going to be bottoms up. So I look at bottoms up, and then I say, where does the graph start existing? So the graph starts existing right here at 1, and that's definitely included. So that means brackets 1. And then don't get confused. It does kind of trail off right here, but I really want to, it still exists no matter what. So it still exists. It still has something to connect to it. That's what I mean by existing. So it still has something to connect to it no matter what, even if it sort of trails off right there with the open dot. I'm going to continue, continue, continue. Where does it stop existing? At 5, and that is going to be a bracket. Awesome. X-intercepts, none. Y-intercept, it actually is 1 y-intercept. It's 1. Okay, f of -2, I look at -2. Okay, that's my x. I see where does it go, and actually it is 5. So that is 5 right here. Sweet. We're going to town on these. All right. Now, the next one is going to be a little bit funky. So I'm going to do that for you. And then the next one, I'll have you guys pause the video, see if you can do it yourself, and then we'll wrap up. Okay? Let's erase. So this one is a little bit funkier, and the reason why it's a little bit funkier is because it's what we call the step ladder function. It's also called the interval function. So it's actually a function that looks like this. Okay, it's really, really funky. All right, in calculus we do a lot of that kind of math, but we can still do the domain and range, but it's a little bit just different. What's my domain? Where does the graph start existing? It starts existing on my x-axis at 1. And that's included. And just because it kind of step ladders up here doesn't mean anything, okay? It means there's always something to connect to it. There's always a solid dot to connect to it. So that still exists. It still exists. It still can connect to something, right? It still can connect to something. Where does it stop connecting to something? 4. That's where it stops connecting to something, and that's going to be parentheses. Let's go to my range. My range is a little bit more complicated, and because it's horizontal where my numbers are supposed to be. So when I look at my range, obviously it doesn't start existing until here. It doesn't exist down there. It exists right here at 1. So I know I'm going to have 1 or something, but watch. 1, and then it doesn't exist at all from here to here, right? It starts existing again at 2. So it's like a whole new thing. So I'm going to say 1, comma, 2. Same thing here. It actually stops existing and then doesn't start existing again until 3. So, comma, 3. And this is what I'm going to do. I'm going to put fancy braces around it. This is actually my range. It's a really, really, really weird range. Excuse me. Whew. Excuse me, it's a weird range, and so that's why I wanted to go through that with you. Let's look at the x-intercepts. Is there any x-intercepts? No. Is there any y-intercepts? Obviously not. And then f of 3, where does f of 3, where does that actually equal? It doesn't equal here because that's open. It doesn't hit a graph until you get to 3, so it's actually 3 here. So that one's a little funky. I get that. Let's erase. Move on to the next one. This is our last one. I want to see if you guys can do it by yourself. So go ahead and pause the video, see if you can get the domain, the range, the intercepts, and evaluate for me. Okay, so now domain interval notation. Where does the graph start existing? It's kind of a trick question because if I read it left to right, this has an arrow, which means it's going on forever to the negative infinity side, which means where does it start? It starts existing at negative infinity. Why isn't that a bracket? Because you can never equal infinity. Okay? Comma, where does it go to? Left to right, left to right. Where does the graph stop existing? It stops existing at 4. And since that's included, bracket. Okay? So if you got that, awesome. Range, where does the graph start existing from bottom to top? It starts existing from bottom to top right here. So what is that y value? It's 0. And it is going to be included because it is a solid dot. And then where does it actually end? This one's kind of a little interesting. Where does it end? Does it continue going up and up and up and up and up and up and up? I mean, this is kind of shaped weirdly, right? And the answer is yes, it actually continues going up and up and up and up and up forever and ever and ever, which means this is going to be infinity. Can you ever equal infinity? No. So parentheses. Awesome. So what's my y and x-axis? My y and x-axis. So my x-axis is actually right here. We just did it. So, and I just erased it. It's 4. So 4. And what's my y-axis? Intercept right there. It is 2. F of 0, what is f of 0? So f of 0 on my x, this is 0. F of 0, where does it connect to? It connects to 2. Sweet. Awesome. This is, by the way, this for kicks and giggles, this function right here is negative radical x minus 4. That's what this function is, by the way. We're going to learn about this in the next coming weeks, but you didn't need to know that. I hope you had a great time. Let's review everything. So first things first, what did we learn? We learned domain and range. We learned that a relation is a function, and we determined whether or not an ordered pair can be a function. We saw whether or not an equation can represent a function, just briefly though. We evaluated a function. We graphed functions by plotting points, absolutely. We used the vertical line test. We obtained information about a function from its graph. Man, we used all this stuff, and then also we identified the domain and range from its graph, and we identified intercepts from a function's graph. Wow. We did all that stuff in hopefully record time. We're not going to have a quiz this week, so don't worry about that. But what you will be worrying about is the functions homework assignment. We will have a homework quiz tomorrow, just not an actual quiz tomorrow. So I erased the actual quiz, but make sure you still complete your homework because we have a homework quiz tomorrow. Fantastic. If you have any questions, feel free, Algebra 2.1, to hit me up. Don't forget to like, subscribe to C Squared Mathematics. Until next time, I'll catch you later.